Welcome for the next session of computer graphics. Today we will see 2D transformations. The objective is to understand and apply various methods and techniques for 2D transformations. At the end, student will be able to understand and apply the core concepts of computer graphics for transformation in two dimensions. As we have already seen how to perform transformation for the rotation operation. For 2D rotation about the origin in counterclockwise direction by the angle theta, where the theta is angle in radians, the rotation matrix is written as 3 by 3, that is cos theta sin theta 0 minus sin theta cos theta 0 and 0 0 1. But there exists the case where we want to rotate at arbitrary point instead of origin. For example, suppose we want to perform counterclockwise rotation about the point xc, yc shown here. So, in this case, we need 3 steps to perform the rotation about this arbitrary point xc, yc. Let us say there are 2 points P1 which is represented by xy and P2 which is represented by x1, y1 coordinates. And this is the point xc, yc about which we want to perform the rotation with this angle theta. Then the first step is translation to move the point xc, yc to the origin. That is, we will perform the translation of this point xc, yc to the origin. That is, we need to move this point xc, yc to the by xc to the left and by yc to the down. That is, by minus xc factor along x-axis and by minus yc factor along y-axis. Hence, the translation factors will be minus xc and minus yc. Hence, the translation matrix will be written as 1 0 0 0 1 0 and minus xc minus yc 1. Then, the second step is rotation. So, for the rotation at the origin by angle theta, the rotation matrix is written as cos theta sin theta 0 minus sin theta cos theta 0 and 0 0 1. Then, after doing the rotation at the origin, we will move the center point to its correct position. That is, this point which was this xyc which was moved to origin in this step 1, we will move it back to its original position in step 3. So the translation matrix will be 1 0 0 0 1 0 xc yc 1. That is, we will move the point by xc in the x direction and yc in the y direction. Like this, we can perform rotation about arbitrary point like xc, yc in 3 steps, that is translation at origin, then rotation and then translation to move the center point to its correct position. These 3 steps can be combined as follows. So combined transformation matrix will be T1 into R into T2, where this T1 is the matrix to move the point xyc to the origin, then R is this matrix that is a rotation by angle theta, and T2 is this translation matrix to move the point xyc from origin to its correct position. If we keep this first matrix as it is and we multiply these two matrices, then we will get this matrix. And then when we multiply these two matrices, we will get the combined matrix with these parameters. So, whenever we want to perform rotation about arbitrary point xyc by angle theta in counterclockwise direction, then we can directly use this combined transformation matrix. Let us see another operation in 2D transformation, that is shear. Shear is the operation where a transformation that slants the shape of an object is performed. So whenever an object is slanted, maybe in x direction or y direction, it is called as shear transformation. Hence there are two types of shear transformation, x shear and y shear. In x shear, if you observe this object, original object, that is this rectangle, then in x shear the object will look like this after performing the x shear operation. That is, the x shear preserve this y coordinate, that is this vertical height of the object as it is. So this vertical height is maintained, but what is changed is the x coordinate. That is, after slanting, the width of the object will change. That is, the object will be slanted either towards right or towards left. So, for example, if your point is x, y, then your shear matrix for x shear is written like this: 1, 0, shx, which is the shear factor in x direction, 1. When you multiply these two matrices, the result will be x plus shx into y will be the x coordinate after applying x shear, and y coordinate will remain same. This can be performed instead of matrix multiplication using these simple calculations also. That is, x new is equal to x old plus shx into y old, that is this value, and y new is equal to y old because y is going to remain same. Then in the y shear operation, if this is the original object again, then in the y shear operation, it preserves the x coordinates, that is the width of the object will remain same, but it will change the y coordinates such that it causes the horizontal lines to transform into lines which slopes up or down like this. So you can perform this using matrix multiplication. For example, if xy is your point and if you want to perform y shear by the factor shy, then the matrix will be written as 1 shy 0 1. When you multiply this xy point with shear y shear matrix, then the result will be a matrix that is x and x into shy plus y. So this can be performed using these simple calculations instead of matrix also. Then reflection is also one more operation which can be performed in 2D transformation. Reflection again can be performed in different ways. For example, you can perform reflection at x-axis, reflection at y-axis, and reflection in the origin, that is y is equal to x. Let us see reflection at x-axis. In the reflection at x-axis, if this is your object, then after reflection about x-axis, it will look like this. That is, your width of the object, that is all the x coordinates will remain same, but this y coordinate, if it is minus y, it will become y, or if it is y, it will become minus y. This is the reflection about x-axis. If you consider reflection at y-axis, then this object when reflected about this, that is, assume that mirror is kept here, then the object will look like this in the mirror. So your y factors will remain as it is, but what is going to change is this x will become minus x. So in the reflection at x-axis, assume that mirror is kept on the x-axis. In the reflection at y-axis, assume that mirror is kept at y-axis. And when you are doing reflection in the origin, that is at y equal to x, that is at 45 degree, then Assume that the mirror is kept at this line. That is, this object will be reflected like this by the 45 degree. So, if you want to perform reflection at x-axis, then as seen here, this x will remain same, but this y will become minus y. So, this factor will be minus 1. So, the matrix for reflection at x-axis is 1, 0, 0, minus 1. So, if you want to reflect the point x, y, then you multiply it with the matrix 1, 0, 0, minus 1. You will get the reflection at x-axis at x minus y. Similarly, if you want to perform reflection at y-axis, then the y coordinates will remain same, but this x coordinate will become minus x. So, the matrix for the reflection at y-axis is this factor will be minus 1. So, matrix is minus 1, 0, 0, 1. So, if you want to perform reflection of the point xy about y-axis, multiply it with the reflection at y-axis matrix, you will get the point as minus x y. And for reflection in the origin, that is at y is equal to x, the it is the combination of reflection at x and y axis, that is at 45 degree. So x becomes minus x and y becomes minus y. So the matrix is minus 1, 0, 0, minus 1. So if you want to perform reflection of the point xy, then multiply this matrix with this reflection matrix, you will get the new matrix, that is new coordinates, that is minus x minus y. That is, the point xy will be reflected as minus x minus y. These are the few references used to prepare this presentation. If you have any query, please feel free to ask, and do like and share this video. Thank you.